Okay, today we are going to talk about the ceramics. If you remember that ceramics are the first group of the materials with which the civilization began. I told you that it's the old stone age that actually kind of marked the beginning of the civilization and our use of the materials for building various types of artifacts. And so that's the same thing which has come back after thousands of years in a much bigger way into the civilization, and how it has kind of appeared in our civilization and how we are today using it. This is what we will be talking about in this series. So first we will talk about a little bit of introduction, we will talk about the classification of ceramics, and then we will talk about the ceramic crystal structure. Now the name ceramics, as I told you that this whole thing itself is very ancient in nature. The name itself is also having a very ancient root, because it is derived from a Greek term which is keramikos, which means actually burned stuff. And in earlier days, when we used to talk about something like ceramics was always associated with pottery. So clay is the earliest known ceramics which are used in potteries, and that's mostly alumina and silica type of material. Now ceramic materials are definitely by root, they are actually inorganic crystalline materials, that's very important, which are made from compounds of one metal and a non-metal. So if it is a metal non-metal combination, then that type of ceramics are generally having ionic bonds, and if it is non-metal combination, then it is generally having covalent bonds. Now glass is also sometimes uttered in the same way with the ceramics, but glass by definition is not a ceramic, because ceramics have definitely distinct crystalline structure, but glass is amorphous. However, their mechanical properties of glass, even though they are amorphous, they are very much similar to ceramic materials. Some of the common characteristics are both ceramics and glass are hard and brittle. For example, carbon in the form of diamond is known as the hardest material, strong in comparison to tension. It is actually in sometimes it can be something like 10 times stronger in compression than in tension. Chemically very inert. So if there are some chemically active substances, you can very easily keep ceramics or glasses, you can use them to contain. They are known to be good insulators of heat and electricity. In metal, you are always getting free electrons to travel to carry the charges, but in ceramics or in glasses, that's not there. Ionic bond and covalent bonds are very strong to absorb electrons. So they are insulators of heat and electricity. Only exception could be because of the special allotropic form of carbon in diamond and graphite, and generally they have very high and well defined melting point. The melting temperature of course is also quite high in comparison to metals, it is even higher. In fact, that is why many of the re-entry vehicles you will find, like space shuttles and other things that comes back from the space, and hence it is subjected to very high temperature, you will see that invariably they have the surface is made of ceramic tiles, so that it can resist the high temperature. There are many examples. For example, the silicon carbide, which is used as abrasive grinding wheel, or you will see it even in the disc brakes. then silicon nitride, which is used in rocket thrusters, uranium oxide, which is used in nuclear fuels, porcelain, very standard in high voltage electric insulators, titanium carbide, space shuttle heat shield, zinc oxide as a semiconductor, sunscreen, or sometimes even in cigarette filters. Bearings, you will get silicon nitride again, boron nitride in crucibles, and of course lead zirconate titanate, one of the smart materials which is heavily used in the ultrasonic transducers. So, all ultrasonic tests, when you see the crystal that is used inside to generate a high frequency vibration, that is nothing but a piezoelectric material, which is a ceramic material. Now, let us go for different types of ceramics. So, first of all are the natural ceramics, for example limestone, which is mostly calcium carbonate, sandstone, which is largely silicon dioxide, or granite, which is like aluminum silicate. So, there is a very good actually reserve of ceramic materials in the form of rocks and stones. Next is abrasives. Typical examples are like silicon carbide, tungsten carbide, alumina, also known as corundum, silica sand. They are used to grind or cut away other relatively softer materials, and they generally, because they are used for cutting away or sharpening other softer materials, so they have actually very high hardness and wear resistance, and they are used in the form of, for example, bonded to grinding wheel by glassy ceramic or an organic resin, something like tungsten carbide wheel, or abrasive powders coated on paper or cloth, something like sandpapers. So, in the form of abrasives, they have very large applications for sharpening or shaping or making smooth the texture of various types of products. The next, one of the biggest application of ceramic materials is in the refractories. For example, they are used in furnaces operating around 1500 degrees centigrade. If you look at the brick kilns where the bricks are prepared, that the kiln itself is made of refractory grade of ceramic materials. With they can, as I told you, that they can withstand very high temperature without melting, and they remain unreactive and inert under severe environments. That is why in addition to not getting molten, that inertness makes it suitable for many processes where there are corrosive chemical environments are generated. There are many examples of them like alumina, silica based bricks, fire clay, zirconia, magnesia, or periclase. So, there is a fire clay which is a combination of alumina and silica, or there is a zirconia. I will talk about zirconia later. So, there are many such things, and if you look at it in terms of compositions, suppose fire clay, you will see that most of it is actually alumina. More importantly, of course, silica is also there. In fact, silica is higher than alumina, and then magnesium oxide, little bit of iron oxide, calcium oxide, and titanium dioxide. If you look at the high alumina fire clay, 90% is alumina, then 10 to 45 the silica may vary. Again, little bit of magnesium oxide, iron oxide, and calcium oxide. Similarly, silica, you will see that mostly it is silica itself, alumina comes as an impurity there, then of course magnesium oxide and calcium oxide. The other important thing is that the porosity is generally about 20 to 25% in this type of materials. So, they are porous, and that can reduce the weight of the system at times. In fact, one of the silica one of the ceramics that I have shown you earlier is actually xerogels or aerogels. They are very light because they are highly porous. Okay, so this is also good for various applications point of view like thermal insulations. The ceramics as composites. Okay, so when we will discuss about composites, we will discuss about ceramics in terms of fibers, also ceramics in terms of matrices. In general, ceramics are very important elements of making composites. You can combine it with metals or polymers to make the composite, and they are done to take advantage of individual component properties. For example, as fibers, ceramics has quite high modulus of elasticity, so you can take advantage of it. And also you know that in a macro scale ceramics are generally very brittle, but if you draw them in the fiber form, then they are not so brittle, and because they are less susceptible to cracks, and hence they are very good reinforcement components in composites. So in ceramic composites, like fiberglass is one of the important things, which is a composite of glass and polymer used for high performance structures. CFRP, carbon as again a reinforcement in the polymer. Cermet, tungsten carbide is used with cobalt, and that is used in cutting tools. Bone, our human bone is one of the best example of ceramic composites, where you have these collagen fibers. So collagen here works like a fiber, and hydroxyapatite works like a matrix. There are many new ceramic composites coming up, like alumina silicon carbide, which has high temperature and high toughness applications. The other vast examples of ceramics are actually the cement and concretes, which is used as construction material, and the cement is basically a mixture of combination of lime and silica and alumina, and it sets when it is mixed with water. The concrete is mixture of sand and stones, which are like aggregates which are held together by the cement. Okay, so in that sense the stones work like you can say as particle reinforcement in a macro scale, a kind of a similarity to composites. So they work like particle reinforcement, and the cement, the ceramic part of that is like the matrix in the whole system. So cement and concrete is another very good example of the ceramics. Now there are certain high performance ceramics which has a high resistance to fracture and temperature stability, high load carrying and wear resistant properties. For example, the dense alumina, which is used in cutting tools, dies, wear resistance. Then the silicon carbide or silicon nitride is used for surface bearings, medical implants. There is another product which is known as sialons. It is a complex composite of silicon, aluminum, oxygen and nitrogen, and sialons are also used in various applications in engineering like engine and turbine parts. Then there is the cubic zirconia, which is used once again in terms of making cutting tools, dies and armors at times. So these are high performance ceramics. The high performance comes because one has to really it has to undergo very complex chemical processes, okay, are not unlike your cements and concretes. In this case the ceramics are actually, in one of the examples I will show you that the minerals are first excavated and then they are very highly filtered, sieved and only the pure ceramic materials are actually chosen, and then there is a processing, and then you make the green sample, finally you burn them and you get the sample which you use. So, all these process which makes it very expensive, as well as it actually yields very high performance parameters to the ceramics. Now, glasses, as we have said, that they have some very common properties with ceramics, although they do not have regular crystal structure, but they are amorphous in nature. Now, the glasses are actually non-crystalline silicates, maybe from calcium oxide, sodium oxide, potassium, aluminum oxide, etc. Many a times actually we make a something which we call eutectic mixture, so that the temperature required to melt it, because the key thing is that you have to get various types of oxides in a stoichiometric ratio, and you have to heat it to a high degree of temperature. Now, if that temperature can be reduced, a good stoichiometric ratio can actually give a eutectic temperature which is lower, and then the whole thing melts, and after melting the cooling process, this as you can see here, that from the liquid, if you hold it for a long time at a particular temperature level, then the crystallization takes place and you start to get crystalline solids. But instead of holding it, if you start to cool it, in fact the faster the better. Okay, that means you are simply freezing the fluid, the molecules are moving all around, and that mobility is suddenly frozen, and then that will give you the amorphous glassy structure, and that kind of glassy structure also gives you beyond Tg, it gives you a very brittle structure, mostly because there will be lot of micro cracks that will be there in that super cooling condition. Now, these glassy systems can also be made crystalline by a high temperature heat treatment. So, once again you take it to a very high temperature and then hold it and get a crystalline form. This is commonly known as glass ceramic. So, there are two very common type of glasses: soda lime glass, which is used in windows, bottles, and easily formed and shaped. The other one, which is more expensive, is borosilicate glass, and that has actually, along with the silica, it has actually boron oxides, and this is used for pyrex, cooking and chemical glassware, high temperature, strength, low coefficient of expansion, and good thermal shock resistance. There is a fascinating variety of ceramics which is known as piezoelectric ceramics. We will certainly devote more time on this, but this is just the beginning of introducing the ceramics. So, I will talk very briefly about it now. Now, these ceramics are capable of actually generating electricity. For example, if you apply mechanical force into it. So, you can see it here that you are applying mechanical force and there is a voltage that is generated in the system. This was actually discovered by the Curies, and quite a century before, but now it has lot of industrial applications because of the piezoelectric effect, which is very prominent. We call it giant piezoelectric effect actually in some of these ceramic materials. For example, barium titanate, lead titanate or lead zirconate titanate or potassium niobate. So, some of the materials where this effect is very predominant. So, there are two types of these piezoelectric effects in these ceramics. One is direct effect, which is used for sensor making, like in your many of these cameras you will see it, that if there is a stress, then there is a electric voltage that will be generated on the system. And the other is the reverse effect. Okay. That means you apply the electric field and you are going to get strain out of it. The applications are enormous. Some of them are inkjet printing head, ultrasonic testing, strain gauges, various types of sensors, various types of actuators are developed using this piezoelectric ceramics. But there are some very special grade of ceramics. Now we will discuss about the bonding and crystal structure of ceramics. Now as I told you that this bonding in ceramics can be either ionic or covalent bond, or can be both actually. So depending on the typical compound, you can actually find out that what is the percentage of ionic character. Okay. So that means if you know the elements that are used in the ceramics Xa and Xb, and if you know the electronegativity, then you can find out that what is the percentage of the ionic character. For example, calcium and fluorine, you know their electronegativity, so you can find out that it will be 89% ionic in nature. On the other hand, silicon carbide, you will see that it is mostly covalent bond predominant, so it is about 12% of ionic character. So the compounds, the elements that makes these ceramic compounds, their electronegativity basically determines that whether it is going to be predominantly ionic bond or whether it is covalent bonding. If they are very far apart, that means if Xa minus Xb is very high in the electronegative, in terms of electronegativity, then it will be predominantly ionic. Otherwise, it will be the other way around, that is covalent bond. There are very popular examples of ionic ceramics. The common salt that you take is the ionic ceramic, sodium chloride. Then of course magnesium oxide, zirconia, alumina, these are all ionic ceramics. They have actually a metal non-metal combination, and that is what makes these bonds actually the ionic bonding. And they are generally, because there is this electrostatic attraction between the unlike charges, they have very dense packing. So the density could be very high. So this is the structure of common salt, rock salt, sodium chloride, as you can see. Then magnesia, cubic zirconia, which is little more complicated, and alumina. So that is about the ionic ceramics. Now if it is two non-metals, for example carbon and silicon, then it may create covalent ceramics. So here the bonds are formed by sharing electrons with its neighbors to give a fixed number of directional bonds, because covalent bonds are directional in nature. For example diamond, silicon carbide, or silica cubic structure. Because the bonds are directional, that means these materials, even though they are strong, they will be anisotropic, because they are along the direction of the bond you expect more stiffness than across the bonds. Now some ceramic structures, crystal structure wise, are actually more stable than the others. Why? Because if you look at the ionic bonding based ceramic structures, then you have cations and you have anions, and generally anions the cations are actually smaller than the anions, like there is a cation here and all around there are these anions here. Okay. So because this fellow is there in the middle, there are various ways in which you can get a three dimensional structure, but the most stable will be if they are in touch with each other. If not, for example in this case they are not in touch with each other, as you can see these regions. So that is also, that may not give stability, and definitely if this happens that the anion is not touching the cation, then definitely there will be an unstable situation in it. So let us look at it with much more variations. For example, from the coordination number point of view, if there is a linear structure, then we get a coordination number of 2, of anion cation. If it is a planar equilateral triangle, something like that, you get a slightly higher coordination number, you get a better packing. If it is tetrahedron, that is, you can see that all 4 of them and the anion is sitting inside, you get a better coordination number, even better. Octahedron 6 or cubic, you get the maximum about 8. So that is how the packing actually changes, and depending on various types of cation anion combinations, you get actually various types of packing systems. It can go as high as up to 12 in fact. So we have shown here up to 8. The common crystal structure in ceramics is actually AX type of a crystal structure, where there are equal numbers of cations and anions, often referred as AX compounds, where A denotes the cation and X is the anion. For example, zinc sulfide, equal number. So, and the coordination number in this case is 4. All ions are tetrahedrally coordinated. There can be other examples like silicon carbide or zinc with thallium. So, these are similar to zinc sulfide in terms of AX compounds. Another type of X compounds are sodium chloride, okay, rock salt, and here the coordination number is higher, it is about 6. There are other examples of these type of rock salt structure like magnesium oxide, iron oxide, etc. Then cesium chloride is the third type of system which has even higher coordination number among the AX type of structures, and there are both types of these systems, both shows close to 8. So, this is the highest coordination number in the AX structure. Now, the other possibility is actually AMXP type. That means you do not have equal numbers of cations and anions, you have unequal numbers of them. For example, calcium fluoride, zirconia, okay, thoria, etc. Many of these radioactive materials, they belong to this group, AMXP group. And the third type, which is even more complicated, is actually AMBNXP group, where you get actually more than one type of cation. Like in this case, you get barium and titanium, 2 cations, and oxygen as 1 anion. So, this is also known as, I told you earlier that this is also known as perovskite, named after a Russian geologist, and many piezoelectric materials actually show this type of 2 cation system, AMBN XP type of a system. Now, how do I use this to compute theoretically the density of a ceramic compound? So, the informations that we will require there is that, first of all, number of ions in the chemical formula. I will explain soon with the help of an example, and then sum of the atomic weights of all cations, sum of the atomic weights of all anions, unit cell volume, Avogadro's number. So, let us look into this particular example, that can we find out the theoretical density of sodium chloride, okay, rock salt. What is known to us? What is the atomic weight of sodium? That is 22.99 gram per mole. What is the atomic radius of sodium? That is also known to us, about 0.102 nanometer, 0.102 into 10 to the power minus 7 centimeter, whatever way you put it. The atomic weight of chlorine is 35.45 gram per mole, and atomic radius of chlorine is bigger. This is about 0.181 nanometer. So, this is the anion which is bigger. So, as you can see here that these are the green ones are the chlorines, okay, that is your 0.181 nanometer, and the orange ones are the sodiums. Okay. Now, number of ions in NaCl are actually 2, okay, Na plus Cl minus, and if A is unit cell edge length, then what is its volume? If you look at it, that if you look at the structure of it, as you can see here, that this half and this half makes it as double of radius of the sodium atom, and then a full diameter of the chlorine. So that is the unit cell size. So the cube of that is what is our Vc. So now we can find out what should be the density. The number of ions is 2, that is fine. The atomic weight, if you look at it, cation and anion. So you have 22.99 gram per mole of sodium, 35.45 gram per mole of chlorine of equal proportion. So I can sum it up, and then the size wise you have the that is the size, okay, that is the unit cell size multiplied by the Avogadro's number, because here you have these in terms of moles. So the number of that comes in the Avogadro's number, the number of molecules, so that you have to actually divide, and then you are getting the sodium chloride density as 2.14 gram per cm cube, and the actual experimental value is about 2.16 gram per cm cube. So that means we are pretty close in terms of the estimation of sodium chloride in this manner, provided you know that what is the chemical formula of a material and you know what is the crystal structure of the material. You can actually find out what is the theoretical density of a compound. Okay. So this is where I think we will put an end, and in the next lecture we are going to talk about the mechanical behavior of ceramics. We are going to talk about its failure and processing of various types of ceramic materials. Thank you.